Hello everybody, welcome back to From Rhythm to Algorithm. Today we'll be discussing more physical intuition, empirical facts, and building out our theory and continuing towards our derivation of the axiom sensorality with an S. Today will be mostly structured physics, showing you how vibration and rhythm, and discussing how those physical principles and those physical phenomenon relate to current theory, specifically to electricity. We're discussing the photoelectric effect. Last physics video, we discussed, if you want to go watch the episode, it's titled Boundaries and Axioms. We started with our physical boundary conditions, literally empirical things that are true for anybody, you can't deny them. The first two are about prime numbers and number fields, which again is really, the formality of my thesis. The written part is more to show how what I have done touches up on every bit of theory, inconsistency in theory known today, and really that they were asking the wrong question. Again, we discussed how the motivation to unify physics is really the bad thing, is really misguided, not bad. But today we'll be discussing all about the electron and electricity. I'm showing how our ideas and our axioms apply to those, specifically to, I believe it was the fourth one, but the one about the photoelectric effect and with the continuous pressure gradient. Again, we have a continuous pressure gradient. Again, it's like when I say stabilization, right? In the same way you learn something. You struggle with an idea, then the light bulb moment, the aha moment clicks, and then you can't forget it, right? You might be rusty, but you don't learn how to forget to ride a bike. And so, again, the universe is the same way, where it kind of stabilizes into different things, or stabilizes different properties, vibration into light into mass. Those events have stabilized, those are in the past. And now today we are in R3, we're in a continuous pressure gradient. And so instead of talking about force, right, pressure is force per unit area. And so now we've discussed it at length, the specificity and generality, and physicality to sensorality with a C, without sentience. And so the stabilization of energy of light into mass, that's where the photoelectric comes from. The vibration, you vibrate an atom at a given frequency, that frequency excites an electron, and then when that electron goes back to its ground state energy, it dissipates that energy in the form of a photon, and that's called scintillation. So what we have there, the evidence of that word existing, a word that I have not derived or axiomatized myself, scintillation is the condensing of logic of literally the words photoelectric effect. You have the physical phenomenon of that electron going up in orbital, coming down and releasing the photon, and you can see it if it's in the visible light spectrum, or detect it with some sort of radiation if it's outside of the visible light, or for just to the naked eye. But that word's existence, and they both describe the same physical phenomenon, photoelectric effect or scintillation. They mean the exact same thing. And so you've already condensed the logical meaning and intuition of what the photoelectric effect is into the word scintillation. And so that was an important linguistic thing. But again, my paper itself touches up on the boundaries. And then when you do a first principle proof, when you start with an empirical fact, it has to relate properly to other theory because you didn't start with somebody else's. You didn't start with an inconsistency. If you really do every step one by one, you can't create a conundrum. And when you solve a big open theory problem, what you're really doing is resolving contradiction, as opposed to doing a calculation. Anybody in actual theory will know that. Anybody up until even graduate school. I mean, if you haven't done real research, if you haven't done a proof yourself to any level, you haven't really been exposed to mathematics whatsoever. And what I'm doing is deriving an axiom, which is the highest level of generality. But so we have, what is electricity, right? Electricity is the flow of electrons. So again, in electricity and magnetism, or in physics, we talk about the mass of the electron or the charge of electron. The units they will use, again, dimensionless analysis, that's what we're doing. Again, vibration has no dimension. It's relative to the vibration around it, a decibel. But what was I saying? Oh, the electron, using the mass of the electron and the charge of the electron as the unit 1, as opposed to relating it to something and using the Coulomb to relate it with the mass or whatever you want to do in terms of energy. But so just mass of electron, charge of electron, standard, that's how they do it. Theoretical physics is taught right now today. But electricity is the flow of electrons. So you have some material, you have a chunk of gold, a very good semiconductor. What's a semiconductor? A material that conducts electricity with what are considered standard conductors and as well as insulators, which as opposed to just conducting electricity with conductors. And so what makes a conductor? Well, again, something that the electrons can flow. You've heard when we were in school, you've heard the term sea of electrons, right? So you have your nucleus, your positive and neutral charges, just to stay with the consistency. But again, neutrons don't exist. There's still a charge distribution inside the neutron. But again, remember, we have our fundamental density limit and size limit with the bounding of the 3 quarks based on our energy scale, what we can probe with our energy levels and our equipment. And the electrons are bounded to that in a stable dynamic. We talked about the iron catastrophe last video briefly linguistically, but we have our atom, the electron clouds whizzing around, but there's free electrons, and then it stabilizes. You have the orbital levels of your electron, which once you have a stable orbital, it is shielding. The shielding is the term they used, but shielding the other electrons that are further from the nucleus away from the strength of the positive charge. So further away from the nucleus, the less strong the attraction is, simply because the distance as well as the complete orbital levels, those complete shells, negative charge to negative charge repulsion. So those electrons are the ones that flow. Hence, in the empirical fact is that you have surface charge is what produces the flow of electrons, hence electricity. That's why you have a Faraday cage. If you're not sure what a Faraday cage is, right? The best example or the quintessential example is, right, if you're in a thunderstorm or a lightning storm and they tell you to stay in your car. And a lot of people, or some people, will say, it's the rubber of the tires that, is the insulator, as opposed, which, keeps you safe from the lightning. When in reality it's a Faraday cage. The surface charge, the electricity is traveling around the outside of the car. And so the current doesn't go through you, which would, electrocute you. It just redirects the current, and it gets grounded into the ground. And so that's kind of like the most common, but the point being is these less strongly coupled electrons are the ones that are flowing on the surface of a given conductor, and that is where Faraday's cages come from, and essentially what electricity is. And so we have this big thing in the early 1900s. What's more, late 1800s, early 1900s, not exactly sure. Should know this, but I don't. But what's more useful for our technologies? Direct current or alternating current? You have a voltage. If you look at your outlet on the wall, there's some electrical capacitance. Right? If you change your radio, if you have an analog radio, you're changing your radio as a capacitor. So what is a capacitor? It is an object that has capacitance. It stores electric charge. And so I just have ability to store charge specific to electrical for a given capacitor compared to pressure. I wrote that in. But again, I do most of this off the top of my head. I just have notes if I need to reference a certain word or definition. But again, I'm unifying the logic, so it's not like, it's like taking an open note test in college, where it's like they'll give you the equations, you have to know how to use them. Well, in big boy mathematics, there's data out there, go figure it out. And so, but I pretty much do everything off the top of my head, and it'll be very clear. I mean, it's not like I'm trying to hide my notebook, pad or anything, but because a lot of the time I derive in real time on these things. Pretty much the entire time, actually. But, so why did alternating current win out for direct current, right? All of your house things are indirect current, or at least serviced with alternating current. I don't know if there's a transistor that brings it back down to direct current in the wall outlet, but the point being is alternating current works better for minimizing the inefficiency of transferring electrical power over large scales because of rhythm. that is physically, empirically evident as why alternating current is better for transmitting electricity long distances. It's because the rhythm preserves the dynamic of transferring the electrons. It preserves the momentum literally. Again, remember, electricity is the flow of the electrons. So when you turn on your light, it's not the electron from the light switch zooming around. It's the electron that's right there in the load, is what they call it. Whatever burns or uses that power. Again, in your light, you have some filament. The electricity flows through that filament, and it radiates, it burns off, and it emits light. Right? The photoelectric effect, scintillation. And so that's how lights work. That's what electricity is. And that is why alternating current is more efficient at long distances, is because of rhythm. So they have step-up transformers, which is also kind of an analog to a transistor in a semiconductor, or a transistor in a circuit in everyday electronics. Smaller electronics, it's a lot more beneficial or more efficient to use direct current. That's because you don't have to, again, effectively store, or more correctly, you don't have to preserve the dynamic of transferring that momentum over a substantial amount of distance. But direct current charges your cell phone and your everyday electronics. So for smaller scale things, that's pretty much what you use direct current. But the major power grids are functioning on alternating current because of the rhythm increasing the efficiency. But also I have here, I wanted to connect something specific with the words. Electrons are asymptotic, right? So in mathematics, we have an asymptote, a graph representing evolution over time, let's say, of whatever two variables you want, and it nears zero, but it never gets zero. That's the same way in my, literally right now here, me, my notepad, my pen, everything that's touching, everything's connected, nothing is touching, but everything that is connected, exists that pressure. That's the pressure gradient. That's our tension path, our continuous tension path with discrete objects. But the electrons, the electron of my finger is not actually making contact with the electron of the notepad. The electrical charge is just too strong. In the same way you take two magnets together and you push them together and you feel repulsion even though they're not physically touching. And so that's going on there. Again, electricity, magnetism, same thing. Maxwell already did that. But I just have implications for bonds in terms of the sea of electrons. So like how when you turn off the electrons and the electrons are flowing, but as the surface charges and they stop, then you stop it, how do you have the same electrons? Does conducting electricity make you lose mass? Well, it's almost off the top of my head, and certainly because there's nothing that's 100% efficient. And so how much mass, and again, what kind of limits can you do with the efficiency of electricity transfer? Again, that's so empirical and applicable to engineering. You probably already have it out there. You might call it something different. I don't know. But I thought about that. Just does conducting electricity make a given section of material lose mass? I would assume it has to. But I don't have any. Do all of this just based off logic and words. So what other elements do we have, or words and materials that come up for electricity? You have a conductor. Again, that's something that conducts electricity. So first of all, why do conductors and insulators exist? Again, insulators just stuff without free electrons. That's pretty straightforward. But why metals specifically? And again, I guess my assumption would just be a lot of free electrons. But they're solid at room temperature. Some of them are solid at room temperature. So I'm guessing it's more of the environment that regulates what you need, as opposed to something being super special about metal. Again, outside of it just being free electrons. What made metals are environmental conditions. Insulator flow. So a semiconductor, again, is just something that conducts with a conductor or an insulator. A transistor is something that steps up or steps down, amplifies. It amplifies or de-amplifies, or whatever the opposite of amplification is. Dampening. We call it dampening in structured physics right now. It's called the dampening of a spring, boom, 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 where you bounce a ball and it slowly loses potential energy and kinetic energy till it goes to zero. Dampening. So it dampens or amplifies. Again, see, that's like a dichotomistic pair right there. That's what I do all day in my head. It's just compare two words, whether they're similar, whether they're completely different, the same tense of a verb, same form of a word, noun, verb, doesn't matter. And then I just connect them all and theorems pop out. So what is a circuit? It is a closed path. It has a power source, a battery or an outlet. Right? A battery is just a capacitor that's stored up and then you run out. The reason your electricity on your wall doesn't run out is because it's connected to the big power grid that is charging. or that is charged by what other things, burning fossil fuels or wind turbines. Or nuclear reactors, or the other things you've heard in the news. But then you have conductors like wires, or typically wires, and then you have the load, which is the bulb, the light bulb, or the motor, or whatever's burning the power. And so again, you have no 100% efficient engines or machines or anything that does any physical process is never 100% efficient. But what can we say about that? Again, a circuit is a closed path with flow. You have magnetic and analog circuits also exist, so not everything is an electrical circuit, but it's just things that are connected, right? A tension path or circuit will generalize into a tension path. Again, tension being the more fundamental physics word than potential energy. Potential is an adjective. It describes energy, where tension is just tension. It's the proper ontological word. But how about laminar flow? What can we say about that? Because right now we can talk about, we've talked about friction and lag and drag and resistance, right? Resistance in general. So now we can talk about all things that create friction or cause inefficiency. All of those things are resistant. And so we can generalize, or we can, condense all of this logic instead of saying, again, in the same way, trying to unify the forces is kind of a misguided motivation. This is kind of ancillary to trying to unify electricity, magnetism, and gravity, and the strong and weak nuclear forces. It's just like it's the wrong motivation. But we can relate the words in more generality through just the overall general idea of resistance. Because then they'll say, right, and then we have impedance or impotence. Not impotent like you can't have a kid, but impedance or impedance. IMPEDENCE. And it just has the opposition to flow, and that is an alternating current, and they use resistance in direct current. Again, so then resistance, opposition, friction, all of those things kind of mean the same thing. And again, we're just sifting through all of this logic. We're just sitting here churning all of these words until we get to, again, a definitive, unique, axiomatic statement that is true physically. Sensorality is. Nobody can deny the truth. This is our variable, this is our entity we're trying to figure out. What sensorality is at the fundamental level that applies physically. But again, analog circuits, those are just like the Rube Goldberg machines where you put a bunch of different things together and they all hit each other. All right, so that would be like sensoring with a C. Those different things just hit in the different masses, knock the light pole over, and that makes the ball roll, and that falls into the pot and boils the water and causes the next thing. That's mechanical censorship. But laminar flow, again, dancing. Think of dancing, right? The beat sets the rhythm, and you're over there, you're all awkward and goofy, trying to bust a move, pick up some chicks, or some dudes if that's what you're into, trying to get those big wieners. And you're sitting there bobbing, but the tempo, the beat, the rhythm, the pulse is going to set an expectation, a physical expectation value for when you're supposed to move your muscles, literally. So rhythm creates expectation. All right, when you're line dancing, when do you 1 foot, 2 foot, this way, that way? I mean, those are all resultant of rhythm being fundamental physically. Shouldn't be hard to convince you of that. But it creates expectation points. And so you can predict things kind of based off the expectation, right? The phrase, I'm trying to go to where the hockey puck is going to be, not where it was. Again, a super slang way of saying, I'm trying to predict what's going to come next, not focus on what's happening now. And again, resultant of rhythm setting expectation. But current is flow, and so we can talk about flow and current, kind of, again, just different levels of generality and context in which they apply. We will review the Navier-Stokes. That solution is in my written thesis, so I'll just go over my whole paper. But a lot of it is, again, like I said, just I like doing these lectures more than I like reading my paper. Even reading it back, it's still completely correct, but my intuition in linguistics has developed so much in the past 8 years that it's like reading a kid's book, my own paper that I wrote, that unified all this stuff for the first time. It's crazy. But we'll go over the Navier-Stokes in another video, and I'll break down the rest of my paper for anyone who's interested whenever I get to it. But let's see what else we got. We have viscosity, right? So now we talk again resistance, right? So now we have resistance to flow is the definition of viscosity. So now we can talk about friction as being viscous or resistance as being viscous. Because again, we're kind of modeling everything after this continuous pressure gradient. Again, I'll talk about the Navier-Stokes stuff, but viscosity, that will probably be the most general word for resistance or impedance or opposition or any of the other terms. We're all intuitively know what they mean. What is the role of concavity in all of this? Again, at certain distances and sizes, you can use the spherical limit, and so one body moving in relation to another body, it's always going to face, again, gravity. Einstein said gravity is a shape, but now vibration is stabilizing into that mass, and so it's kind of, and definitely closer to Einstein's intuition than Newton's, but the concavity, when one thing, right, it has, for lack of better terminology, it's pointing down, the gravitational field's pointing down over here for this body, and it's pointing down over here for this body, and they're about approximately the same size, but there's no approximation you can use. And so they're both bodies are interacting with concave down systems, right? The gravitational field for here is going to curve, point down for here, and it's going to curve and point down for here. What do you do with that? I don't know. But concavity, again, just another word in generality that's come up in my derivation, touching on that. Don't really know what to do with it or what to say. Can't say anything poignant or insightful. Harmonics and wave dynamics, again, really modeling the environment as, a chunky liquid is kind of what we're doing now. But what is a harmonic? It's just an integer multiple of a baseline vibration or baseline frequency. If you have a guitar string and it's vibrating at a given frequency, however many hertz, let's say 1 hertz, and then it goes up to 2 hertz, that's a harmonic. The 2 vibration is a harmonic of the 1 high vibration, the amplitude, it's an integer multiple. And so that's all that is. But that's what I was saying, where if you throw a rock in the pond here and another rock over there, and the waves, the ripples hit each other, and then they start rippling other places, that's the interference pattern of quantum mechanics, and that's, it's literal to pilot wave theory. I mean, that was another thing that came up in the history development of physics that was really intuitively kind of on to something correct about quantum mechanics not being a unique domain, and then just viewing the double slit as a smaller scale pilot wave was very, very correct or logically useful. But that's really that. Again, harmonics just being integer multiples, and then wave dynamics, kind of viewing, again, the environment you're in right now as a chunky liquid with just different densities. And again, you can local systems like eddy currents in a river. You have your overall big river, but you have different little swirls here and side currents here, and that's kind of how you have your different local fields, electric fields, gravitational fields pointing different directions, but all being a part of the same thing. And so finally, we just have an example of momentum amplification, transistors, speaking about electricity and magnetism dynamics. The transistors literally in the circuits and the semiconductors, or in the circuits with the semiconductors, to allow your phone to have a big, powerful camera that was impossible 50 years ago in its entirety and inconceivable 100 years ago. But also, like mechanically, or an analog situation of momentum amplification, I'll try to find a video, but if I can, I don't get copyrighted or whatever, so I might not put any visuals or graphics. But just deadlifting, like weightlifting, barbells in the gym, woo-woo, do you even lift, bro? Like the deadlift. You can see, just Google deadlift bouncing to lift or something. Deadlift bounce. But what they'll do is they'll literally generate a rhythm. Like the barbell will be loaded up with weight they can't lift, and they would never be able to lift in a competition, but they generate a rhythm, and then they're able to bounce up the barbell into a complete deadlift. If they were in any sort of competition, they'd be laughed out of the universe. But the point being is that's a mechanical, an analog situation of using rhythm to amplify, or amplify momentum, or what did I say? Momentum amplification. Yeah, so that's just an analog example of momentum amplification. So that's really what I wanted to cover now. I have another episode worth of logic and linguistics done. We'll see if I get that. But we covered scintillation. But I'll save the other. There's a couple more bits of physics, but I'll cut this one off here, and we'll jump back into some logic and some leftover physics. So thank you for watching, and I will see you on the next one.